Hi, let's continue now with spatial graph convolutions after spectral graph convolutions. So spatial graph convolutions try to address some of the problems that spectral graph convolutions have in the context of deep neural networks. The basic idea is to approach graph convolutions on the spatial domain. So see convolutions as local matrix multiplication. So we've got our neighborhood, we've got our locality. This neighborhood contains nodes, and these nodes contain features which can take the form of a lower rank matrix, like a subset of the rows from our whole features. Can we formulate our local convolutions as some sort of matrix multiplication, some local matrix multiplication? Here we've got our graph, and given the central node, in this case number 6, we've got all these one-hop neighbors. And if we check the adjacency matrix, these correspond to the highlighted entries in the matrix. So what graph convolution neural networks do, in short, is that they multiply the adjacency matrix with the node features, and in the adjacent matrix only the relevant neighbors are highlighted, right? So this means that only those particular rows in our feature matrix are going to be activated, let's put it like that, and then they're going to be multiplied by our parameter matrix W. So these are our so-called filters right now, like what we would call filters in the convolution neural networks, right? And so, in this operation, the result of this operation passes through a nonlinear activation, like ReLU, and it returns, one new row in our next layer's feature map. So basically, graph convolutional neural networks do left multiplying with the adjacency matrix, such as to recover the features in the neighborhood, and then right multiplying with the weight matrix that we are optimizing for, actually. This looks sort of like convolution because it is an operation where, given the central location, so node number 6, you define a neighborhood, and then you're performing some sort of element-wise multiplication in that neighborhood. This was a simple operation for a single neural network. Of course, this can be repeated, this can be stacked, and therefore we can have like deeper cascades, so deep graph convolutional networks. Basically, there is no little difference. So what is, of course, here interesting to note is that the graph structure remains the same, right? So there is no pooling. Every other layer retains the same graph structure. The only difference is now that our graph nodes obtain different types of features depending on the intermediate parameters, like filter W, W1, W2, and so on, and of course the nonlinear activations. What is also quite interesting to note here is that we have still the notion of the effective receptive field, right? So node 6 affects all nodes in the neighborhood, or conversely, all the nodes in the neighborhood affect the feature of number 6. So in the second layer, the feature of number 6, has already integrated features from the one-hop neighbors, and the one-hop neighbors have themselves features from their own one-hop neighbor. So the effective receptive field, so to speak, of the graph neural network expands in a similar way like for convolutional neural networks. Graph attention networks are having basically a similar idea. The problem with the graph convolutional neural networks is that because of the permutation invariance, so the graph, for the graph, we don't really care about the order of the nodes in the matrix. We're going to have different matrix every time for every different ordering, but effectively it's the same graph, right? So they're all equivalent, that is. This means also that because of this reason, because we've got no sense of directionality, where our weights are shared across edges. So in order to actually account for different types of weights, graph attention networks can help there. So specifically, we're going to now for our nonlinear, so for our nonlinear activations, we're going to first sum over the neighborhood using weight factors, weight coefficients, and these weight coefficients are computed using self-attention weights. So specifically, the attention is basically a softmax of self-attention weights. So the self-attention weights measure the relative importance of every pair of nodes, and the final attention is a normalized version of that. The self-attention has its own parameter U to basically to find a good fit, right? Like to find good parameter, we need to find good parameters so that to figure out how to determine which pairs are important and which are not. And by multiplying the self-attention weights, so the attention weights with our neighboring inputs, we're basically, it's basically equivalent like saying that some of our neighbors are more important than the other neighbors, right? Whereas for graph convolution neural networks, that was not the case per se. And yeah, the self-attention for graph convolutions looks very similar to the self-attentions as we saw it before. Here we're having the sort of feeding feature for the pairs of our nodes multiplied by W, and then this brings us our final attention value. Message spatial neural networks are again a generalization such that we have a general aggregation function defined over our nodes. And one more important concept is that while graphs are, most of the times, more often than not, we don't pull over them per se, or at least many models don't have this notion of pulling. We can actually coarsen them and then have some manifestation of pulling like we would have for convolutional neural networks. So basically, in that case, we group nodes together, and we can even do learnable pooling. The adjacent matrices can get updated, and then we can do average or max pooling. So for instance, if we know that these two nodes belong together, then they become one in the next stage after the coarse pooling. The green ones become one, the blue ones become one, and so forth, right? Again, all this can be merged, and all this can be merged. And by doing this successively, we learn how to coarsen our graph. And this is it for today's lecture. So we discussed what makes graphs special. We discussed how to. We basically went deeper into graphs. What are special properties? What makes graphs, like what kind of mathematical properties graphs have? We revisited convolutions in terms of Fourier transforms and discrete Fourier transforms, as well as translation and equivariance. We discussed how, inspired by the Fourier transform, we can generalize our convolutions such that we support spectral graph convolutions for graphs, and we finished with spatial graph convolutions. Thank you.